Okay, in this video we're going to look at the voltage follower, and then I'll go on to look at the summing amplifier. So the voltage follower then, not a lot we need to be able to do. One of the first things we need to do, as same with the others, is draw the circuit. We'll do that and we'll just show its characteristics. So there we've drawn the circuit, the input going to the non-inverting terminal, and we've got the output there, and we've got 100% of the output going back to the inverting terminal. So we've got 100% negative feedback going on there. So V out equals V in, because when it's not saturated, then the negative feedback tries to keep the two terminals exactly the same voltage. So these two terminals are exactly the same voltage, then the output must equal input, which means the gain must equal 1. Okay, and we can draw a little characteristic graph of that as well. So here we have our characteristic graph. So positive gradient, 1 volt in, 1 volt out, 2 volts in, 2 volts out, a gain of 1, and that line will continue all the way up until the point at which the output saturates. So there's a dotted line. So some of you might say, well, what's the point in it? Well, one of the good things about a voltage follower is that it's very, very good at acting as a buffer impedance matching between stages. So we build electronic circuits, and when we connect them together, there's an interface connection issue, whereas actually this can isolate between the two stages, because if we make the assumption that no current flows into the input terminals here, therefore it must have a very, very high input resistance impedance. Means that therefore all of the voltage from whatever system subsystem we've got feeding to this is going to be seen here, and it's also got a low output impedance. Good for impedance matching. There we have it. Okay, we'll go on to talk about a summing amplifier. So we need to talk about and be able to draw a summing amplifier. So let's draw a 3-input summing amplifier, and then I'll put some values on. So 3-input summing amplifier. A little bit of a clue: it's based on an inverting amplifier. So there we have a 3-input summing amplifier. Okay, so just based on an inverting amplifier, like I said, 3 input resistors and a feedback resistor. Okay, so for any further work, I'll give you some values, and then we can then work out what output voltage we're going to get from this. Okay, so I put some values on: 30k there, 3k, 15k, 10k, and our input voltage is 1.5 volts, minus 4 volts, 1 volt. Now obviously they would normally be wiggly signals, but even with a wiggly signal we have an instantaneous voltage that we can look at, so a voltage at a particular point in time. So let's tackle this with the two methods, voltage and current. Okay, so this is the standard formula for our summing amplifier. It's based around focusing on the current, so the current flowing in this resistor will then add with that current flowing in that resistor, current flowing in that resistor, because as we said on a previous video, no current flows into the input terminals of an op amp, so therefore all of that total current must be then flowing through RF, so it has the same current flowing through there. So through that, so if we can then, once we know what the total current is, we can then manipulate this aspect round to find out what our output voltage is. Word of caution with this: I know some of you like to just bung all the numbers into the calculator, but if you are going to use this formula, work out this current, and then work out this current. So you've got some workings there. So first step, just writing it all out. So we're just putting in the values so we can start to show our workings. Okay, let's work that out. Okay, so we've got all of our currents. Obviously we've got a slightly little bit of rounding going on with this one here. So we've got all of our currents, so we can add them all together. And once we've added them all together, then we can multiply by the total currents by the resistor going through to get our minus V out. So I got that far. So V out is approximately at minus 9 volts. Okay, so that's using the current method. Now my preferred method is using a voltage method, which is treating this as an inverting amplifier, but looking at each instantaneous input on their own and adding all of those instantaneous voltages. So you might recall with a normal inverting amplifier, we can work out what the output voltage is by taking the gain of the amplifier and multiplying it by V in standard stuff. Okay, so we can do that for each individual input. So 30k divided by 10k, so we've got a gain of 3. Minus 3, beg your pardon. So minus 3 times 1 volt is minus 3 volts out. Okay. A gain of minus 2 on our second input. Minus 2, so minus 2 times 4 is 8. So 8 volts out. So then on the third input, gain of minus 10 times 1.5, so minus 15 volts. Okay, and then if we add all of those voltages, it gives us minus 10 volts, which is what we got here. Now we got a slight error here, 0.99, because we've got that slight rounding issue here. So not always going to be the case that you're not going to get a rounding error with this one, but this certainly I like this method here because I can see what the instantaneous voltage is going to be. Just my preferred method.